Hello and welcome to Waka Waka Breaking It Down. Today we will be looking at inverse functions, and this is the activity that we will be focusing on. As always, you should always be trying to do this on your own first, reading through it, and then coming to the video to support your learning or understanding, or if you just want a different perspective or want to hear my voice go through it with you. The whole point is very like we've dealt with functions before. Like you should by now know what a function is. So all we're doing now is doing things backwards. Like normally we input an x and we output a y. That's what a function is, right? And we've always said things like for every single x that you input, x value, there's only one y value that you get out of it. So we're going to be doing the same thing, but now when we say an inverse, we're going to be looking at it backwards now. So basically, it's inputting a y value and then talking about the output of an x value. So x's and y's get switched. That's the whole premise of all of this. So let's go through it. The first piece here is looking at an old phone keypad, right? And how you have letters for each number. And the whole idea is like you could use this as programming. So if somebody sent you something like this as a code, not programming, but coding is what I should have said. If someone sent you that as a code, there are options for the letters. So like for the first number 4, I could use the letters G, H, or I. It could represent any of those. So you see down here we have G and H being used to make some words. If I have the number 6, then that corresponds to either M, N, or O. Could be any of those letters. And there's no way for us to know which one. So you see that we used O's here quite a bit, but we also used an M for 6 as well. So you could use an O for the first 6 and use an M for the second 6. So you're just matching these up one by one and trying to come up with some word. So, 4, let's use the G, and 6, let's use an O, and then 6 again, let's use another O. So that would be GOO. And then we have a 3. Oh, I could use a D or an E or an F. Well, maybe I use D to make the word good. Maybe I use F to make the word goof. And you just keep going. So 2s, that can either be an A, B, C. Maybe we use a B for ball, or maybe we use a C for call, right? And then we use an A for the second 2, and for the 5s, I could use a J, K, or an L. So you can see there's some options here, and there's many combinations that you could make of letters, but we're looking for things that maybe spell actual words, right? So here's some good examples of that. So we're just matching up. Now, so if you can see how it's kind of written out for us here. So if there's a 2 as your code number, it could either be an A, a B, or a C, just like what we saw up here. And if I have a 3, that could either be a D, E, F, a 4 could be a G, H, I, etc. So we have that listed out here in a table. And then they say, well, what's the problem with this? Like, and this is getting at the idea of a function and an inverse, which is why we're doing it to begin with. So what's the problem with this? Well, if I put a 2 down as my code, the person who's receiving that code doesn't know if they're supposed to use an A, a B, or a C, right? Because a 2 maps, we say kind of maps over to any of those letters. So that's a problem. Maybe it makes the code more complicated, which maybe is something you want. But when we're talking about functions and inverse functions, we want this what we call one-to-one mapping. For every single one number that you input, we only want one particular output value, and vice versa. For an inverse, we're going to go the other way, and we're going to say, well, if there's an A, I only want a 2. But if there's a 2, I only want it to go to one particular place. I don't want it to go to 3 different places. So that's a problem with this type of scheme, right? So to avoid that, we could, instead of having 3 different letters match one number, why don't we just make every letter have its own number and every number have its own number? Like a 0 is a 0. This is a very simple code, of course, not very inventive. But like it would be more clear. A 0 is a 0, 1's a 1, 9's a 9. And then with the letters, we could continue on. Let's make 10 an A and 11 a B, 12 a C, all the way up to 35 as a Z, and a 36 is a period, and 36 is a dot or a hyphen. Sorry. right? You could do that with anything. I mean, that's kind of how programming would work, right? You don't want to type the letter G on your keyboard and end up getting an H, right? And you want it to match. So, and of course, everything's turned into numbers first, right? Ones and zeros, and then it's turned back into an actual letter. So, yeah, that's kind of the idea of an inverse or a function that we've already talked about. I don't want it to be confusing. For every input, I only want one output, so that it makes it clear. I don't want to have two things going on because it gets confusing. All right, so what would this represent? A 22, oh, you'd have to go and figure it out, but it is an M, right? If you just followed this scheme. A 14, that would be an E, right? 12 is a C, 13 is a D, and then a 14 would be an E. So 14 is an E. 37 is a, oh, they must have that as a repeat then. So, and then 10, oh, maybe they're rearranged. No, 10 should be an A. That's really, what are they? This, oh, I'm like, what's going on? I'm supposed to start over here. All right, so 22, you figure that out. That's an M, right? 14 is an E. 14 again is another E. 29 is a T. And then I'm back at 37 for space, right? And that gives me my space. And then I'm back at 22, 14 again. That's my ME again. 37 gives me my A. Or, sorry, my 37 gives me my space. And then 10 is A. 29 is T, and then I get another 37 as a space, and then 9 is a 9. So meet me at 9, right? That's very clear. And there's no confusion because, I mean, unless you goof it up like I did, but there's no confusion because each letter has its own number and each number has its own letter. That's what we kind of call a one-to-one connection or one-to-one kind of association with each other. Every input for a number has a letter, and for every letter, there's a number. Only one number that matches it, and vice versa, right? So that's one to one. That's when you know that your function or that your equation that you have or your expression is a function, right? But you also know that the inverse of it, when you go the other way, like maybe if I input a 10, that's going to map to an A. That would be like a function because it doesn't map to anything else. And then for the inverse, we're going to look the other way. If I start with an A and I go the other direction, it's going to map to a 10. And that's always going to be true because there's no other number for an A. A is 10. So we would also say that the inverse of this function is a function itself. So the inverse is a function. Okay, starting to wrap your mind around what an inverse is a little bit. Yeah, we're going backwards. This has a low risk of being an incorrect message because it matches one number to one letter, right? One number to one letter. So that's why we like that one. All right, number 3. This is more what I was talking about, right? So for every symbol, there's only one code. And coding scheme 2 works really well, right? Because just what I said, right? For every input, there's only one output, and vice versa. For every output, there's only one input. So let's really define what an inverse is and look at the notation. Okay, so we have our original function notation, the f of x we use, or g of x, or h of x, whatever matches your situation or whatever letter you want to use. When we do an inverse function, we'll use this little -1 symbol up here. It's not really a power. It doesn't represent a power of something. It just represents, well, it kind of does, right? But it just represents what an inverse is. Technically speaking, like if I took an x, which is really just x to the first power, right? And then I took an x and I did to the -1 power. What are you supposed to do with a negative power? Well, you're supposed to do the reciprocal of it. You're supposed to move it to the bottom and change it into positive. So this is the reciprocal, isn't it? Which is kind of like the inverse, right? It's the idea you're inversing something, kind of reciprocating it a little bit, but don't worry about that too much. I just want you to get across the idea that that little -1 just means inverse. We're not actually doing any kind of reciprocals or anything like that. Not at all. It's just a little symbol we use to represent inverse. Okay, so let's look at two functions and talk about their inverses down here. Okay, so we've got f of x and g of x, and we just put some values over here to show where they map to. Like, what values would you get out of it? For example, if I put 2 into the absolute value is 2 because the absolute value changes things into positive. So if it's already positive, it's going to stay positive. If it's negative, then it's going to change to positive as well. So if I put negative 2 into the absolute value, it's going to map to a positive 2 as well. Now for the function, so you can see that some of these numbers are getting used twice. So let's analyze that a little bit. So if we're talking about just a function, like is the absolute value a function? I would have to say yes, because for every input, there's only one output it's mapping to, right? If I put in a -3, it doesn't go to like 0 and -3, or sorry, +3. It doesn't go to two places. I don't have two arrows coming off the -3. Same thing with all these. You can see there's only one arrow coming off of all these. So that makes it a function, right? If I put in 1, it just equals 1. It doesn't equal anything else. It doesn't equal 3 or 4 or something, right? I don't have something like this and this going on at the same time, right? That wouldn't make any sense. So in this case, it really is a function. Like the absolute value is a function on its own. But when you look at an inverse function, now when I say inverse, you see how these all have arrows on them? When I say inverse, in your mind, you have to reverse all the arrows. So all of these end up getting the arrows, and you're kind of thinking about things mapping backwards now, and these arrows are gone. So now this becomes my input. This whole section becomes the input. So I'm saying, well, if I start with 0, does it map to 1 or 2 different places? Well, in this case, it only maps to one place. Okay, great. But when I get to 1, I can see that a 1 maps to -1, and it also maps to +1. There are two different places, right, that 1 would kind of go to if I went backwards with these things. So we would say that the inverse of this is not a function. Sure, I can think about the inverse and I can talk about the inverse, but it's not a function, right? It maps to two different places. So for every input, remember this becomes the input now, it does not have one output. It actually, sometimes it has more than one output. It might have two outputs. So the inverse is not a function. The original equation is a function, but the inverse is not. Now, when we look at something simple like this, now it's actually going to be okay, right? A 1 maps, when I go 1 plus 3, I'm going to get 4. A 2 plus 3, I'm going to get 5, right? Et cetera, et cetera. 3 plus 3 is 6, 4 plus 3 is 7, right? So is this equation an inverse? Or is it a function? Yes, it is, because for every one of these inputs over here, it only has one path. It only goes to one place. So it's a function. But if I do the inverse, now this becomes my input, and I have to reverse those arrows and think about things going the other way and think, okay, if I take 3, right, and put that into the equation, if I take a 3 and think about, what did it start with, if you will, this is only going to go to one place. It's only going to be 0, right? It only goes to 0. If I start with a 4, it's only going to go to one place. And to kind of make it a little more clear for you, what I'm talking about is what x value now the x becomes the output. What x value equals 4, let's say, as an example, equals 4. Well, there's only one x that's going to do that. Like I can subtract my 3 and I'm going to get 1. So that 4 maps to 1, right? It goes to 1. 1 is the solution of that. And there's only one solution to that. So that's why the inverse would be a function. So the original equation is a function, and the inverse itself is also a function. So this one, inverse is not, right? Because of this doubling up. This one, the inverse is. Okay, so that's what this is talking about down here. on part A and B. Okay, and C as well. A little more practice. So let's look at these. Inverses are, is the original equation is a function, and then also is the inverse a function, is what we want to look at. So remember, this is the input to begin with, all your x values. So for any one of these x values that I pick on this first one, does it only have one output? Yes. So this equation is a function. What about the inverse of it? So now you have to think of things a little backwards. Instead of inputting an x value, now I'm going to input a y value. So I'm going to be thinking this way. For, let's say, an 8, is there any other value of 8 that matches the graph? Well, no. This is the only x value right here, whatever that is, that would match up to an 8, right? I don't know what that is, like 3.5 or something, right? Yeah, actually 3.5 is what it is. So 3.5 is the only value that you could input into this equation that would give you 8 out of it. Is there any other thing? Like, can you find any y value that when you look, that it hits the graph more than once? Like it finds a different x value than just one. Well, no, like no matter where you go, no matter which y value you choose, there's only going to be one x value that matches up to that, right? And as we go, you'll see ones that do not work that way. So this first one, the original equation is a function, and the inverse is a function as well. Now, one thing at this point I want to kind of show you is, like, you can think about this in a different way. Remember we said that you're kind of switching x and y's? Well, that's really what you're doing. So algebraically, you can think of it as, like, we started with 2x plus 1 equals y, right? 2x plus 1 equals my y value. If I kind of replace this function notation with y. So what we kind of think about is, like this, you have it equal to y, right? So what we do is we solve for x instead of y to get the inverse. So I'm going to subtract 1 from both sides. Then I'm going to divide by 2 on both sides. And I'm just trying to solve for x. And then maybe I can simplify that a little bit and divide that 2 into each piece on top. And I can see that's like a linear equation, you know. And then what the last step which we do is we switch the x and the y's and think about it just like if it was a equation on its own. And we say, well, what if this was flipped around and this was just a regular old equation, right? So it would graph like this, -1/2 would be here, and then I'd be going up 1 and over 2, and up 1 and over 2, and it would look something like this if I were to graph it out. Something like that, right? So if I wanted, I can find the inverse function itself by switching my x and y and then solving for the y. Or you could, like I did, I solved for x and then I just switched my x and y. It doesn't matter if you switch the x and the y in the beginning or if you do it later. But if you look at this, this is now the inverse equation. This equation that I drew right there is the inverse equation. So what? What are you talking about, Waka? Well, another way to think of it is if I took all my x values and flipped them over and made them y values, or if I took all my y values and flipped them and made them my x values. Because remember, we're going backwards now. So the x's become the outputs and the y's become the inputs. So I'm switching my x's and my y's. I'm switching inputs and outputs. I know that's a little confusing. That takes a little practice on that one. So we'll do some stuff in class with that as well. But that's kind of the point. with an inverse, right, is that you're switching the x's and y's. Let me get rid of all this. Another way to think about it is, it's the same thing I was just saying, but you can think of reflecting, like if I remember we're flipping x's and y's. Like, let me find a point that's on here. Like, this doesn't have very good points. Like if I put in 3 into this equation as an x value right here, right? 3 times 2 is 6 plus 1 is 7, right? So right here I get a 7. So this is the 0.37. For an inverse, the points I'm trying to plot, the x and the y switch. The input and the output switch. So the input now becomes a 7. So I'm looking for the points. Oh, it's going to be hard to graph. But the point I'm going to be graphing would be 7 and then 3. It would be like over here somewhere. Remember we had something that looked like this before, right? So it's going to go through that 0.73. Maybe I should have picked a better point. What if I put in a 1, I'm going to get 3. Yeah, that would work better. If I put in 1, I'm going to get a 3 out of it. So to reverse that, if I put in a 3, I'm going to get out a 1, right? So the 0.13, when you do it as your inverse, then becomes 3, 1. And that's kind of the whole point of working with an inverse. The x's and the y's flip. Things go back and forth. Maybe that part we're going to work a little more with next class and stuff. But for now, you just need to wrap your mind around what is an inverse and is it a function or not. Okay, so let's continue on and we can talk about the other stuff more. All right, so let's look at this. Is the original equation itself, this 1 over x squared, which you can see here, is that a function? Well, for any particular input x, does it only have one y value output? Which it does. I can't find any x value that has like more than one output. I don't see that anywhere. So yes, this is a function. Yes. But what about the inverse? Okay, we got to look backwards now. We have to think, for any particular input of y, is there any place on the graph where it's touching the graph more than once, and I would end up getting more than one x value? And the answer is yes. So unfortunately, the inverse is not a function. So we would say it does not have an inverse function. It has an inverse. It's just that the inverse is not a function. So it doesn't have an inverse function, right? Why? Because if I have the value of, let's say, the y value of 2, I'm going to have this like maybe points. It's like, I don't know, 0.8 maybe or something. And then also maybe like a negative 0.8 or something like that. I don't know. I'm kind of just guesstimating it. So, and that's not even at 2. Well, it might be 2. Yeah, it probably looks like about 2. So for one input, remember the y values are now the input when you're talking about the inverse. So when for one input, then I get 2 different outputs for the x value. Remember, it's the inverse now we're talking about. Okay, so that makes it not a function. The inverse is not a function. So the original equation is a function itself, but the inverse is not a function. And we're going to find out that's true. The same thing over here. If I input a 6, I'm only going to get this one particular y value out of it. If I input a 1, I'm only going to get this one particular y value out of it. There's no other point up here that's part of the graph. So the original equation is a function. But what if we inverse it? What if we go backwards? So let's say input 15. Remember, we're going backwards. So I input 15. Is there only one place that it touches the graph to get an x value? Or is there another one? Well, there is another one over here. I can see that it looks like about -1 and also like at about 7. I have 2 different x values that correspond to one y value. So the inverse itself is not a function. Okay, the original equation is a function, but the inverse is not a function. Same thing here. If I look for, some value right here somewhere, I can see it's going to hit the graph here. It's going to hit the graph here. It's also going to hit the graph way over here. So I'm going to have like 3 different places where that particular output has 3 different inputs, right? Or if we're talking about an inverse, which I'm trying to talk about, then the input for an inverse, which is the y value, has 3 different outputs. So it's not a function. What about the original equation? Is the original equation, is that a function? Well, yeah, because I don't see anything vertically that's going to touch that graph more than once. But horizontally, this is okay. But when I get down to here, then I start touching the graph more than once, right? So that tells me that the inverse is not a function. The quick way of doing these is a lot of times is the horizontal line test and the vertical line test is what we use. But you really shouldn't use that on a test, write that out. You should talk about inputs and outputs. For one input, only one output. For one input of y, there are 2 outputs of x, and that's why the inverse is not a function. That's how you should word it on a test. But a good visual is like, well, if that crosses more than one spot, then the inverse is not a function. If this crosses more than one spot, then the original is not a function, right? That's a quick way of kind of looking at it. And again, we can do the whole solving and find the actual equation that goes along with it, but maybe we save that for later. All right, so this last part is the last part I want to talk about, and this is it for the video. This is talking about, well, could you cut these equations up to make the inverse a function? And the answer is yeah. This one, the inverse was already a function. I don't have to do anything to it. On this one, if I were to just take this piece only and kind of ignore this piece over here, then yeah, the leftover piece would actually be a function, and the inverse of it would be a function as well. Because, if this piece isn't there, then when I kind of check my y value, it's not crossing any more graph because this graph is gone, right? I've erased it. So if this is gone, then any particular y value input is only going to have this one output x value. So that's okay. So if we restrict the domain and either use the left-hand piece or we use the right-hand piece, but not both, then you could have something that would have an inverse function. Same thing with this one. If I were to just cut it down the middle and get rid of part of it, then the part that's left over would be an inverse function, because for every y value, there's only one x value, right? I wouldn't have anything else because this has been erased. So we could restrict the domain and either take the left side of this or take the right side of it only and talk about that being a function and the inverse being a function. But that would really, you'd have to cut your graph in half, right? Same thing on the last one. This is a little trickier though, because it kind of goes up and down. So I could cut it here and just take this piece over here. That would work. I could cut it here and just take the piece in the middle. That would work. Or I could cut it and take this piece over here. That would work as well. Some people say, oh, take this piece. And it's like, nah, that's still not going to work. Because if I just take this piece only, I could have it crossing in more than one spot still. So that's not going to work. You actually have to cut it like here and use one of those 3 pieces. So that's what they're talking about down here, is cutting the domain to get just a piece of it, a little window of it, where the inverse would be a function. Okay. Yeah, takes a little work. The imagery in your brain should be that you're always kind of going backwards. So now the y's become the inputs. If you're talking about a point, that means the x's and y's are switching. That kind of, you can kind of see that up here, right? These used to be the x's and these were the y's, and now we're going to go backwards where where the y becomes the input and the x becomes the output. And some people think of it in terms of this becomes the x and this becomes the y. So that's when you switch the x and y here. Like I had y equals x plus 3. Now I'm switching the x and the y to get my new inverse function. This is the inverse of the original function, right? So that's a different way of thinking about it. And we're going to play around with more of that, okay? But it's going backwards. X's become y's, y's become x's. Just different ways you can kind of think about it. But for now, you just really want to focus on what makes an inverse a function. That's what we're focusing on. Okay, there's a few problems down here for some reinforcement. Always ask questions if you have them. And we also have a practice set. There's a practice set that's posted to go along with it. So you can go through these as well and get a little more practice with this kind of stuff. And there's a word problem here, which is really things that we need to practice. Okay. Always come in for help, and good luck.